Have you ever noticed how a tiny snowflake seems to hold the same delicate symmetry as an entire galaxy? Or how the branching veins of a leaf mirror the sprawling networks of rivers seen from space? It's one of those quiet wonders that, once you start looking, feels almost like a hidden message written into the fabric of reality itself, a whisper of order in what often appears to be chaos. What if these echoes across scales aren't just beautiful accidents? What if they're clues pointing towards something far deeper, a universal blueprint, a hidden architecture that repeats from the smallest quantum flutter to the grand sweep of galaxy clusters? This is one of the most captivating and profound ideas in all of science. The possibility that the universe operates from a single set of rules with patterns that recur no matter where or how you look. From the spirals in seashells and weather systems to the clustering of matter at the largest scales imaginable, we're going to explore how these patterns emerge, why they matter, and what they might tell us about the nature of reality itself. We'll venture into the world of fractals, where infinite complexity arises from startlingly simple equations. We'll see how mathematical constants like the golden ratio appear in art, nature, and cosmic structures, hinting at a harmony that transcends scale. And we'll ask whether the laws of physics themselves might be expressions of a deeper, more universal order. By the end of this journey, you won't just see the universe differently, you'll feel it. You'll start recognizing these patterns everywhere, from the way trees branch to the way light scatters, and you'll understand why this quest has fascinated scientists, artists, and philosophers for centuries. It's a story about connection, about the hidden threads that tie the cosmos together, and about our place within it all. So let's begin. Let's unravel the mystery of the universe's blueprint and discover just how deeply woven these repeating patterns truly are. Look closely at a single frond of a fern, and you'll notice something astonishing. Each small leaflet is a miniature, nearly perfect copy of the entire branch. Zoom in even further, and the pattern continues with tiny structures echoing the same elegant shape. This isn't just a curious feature of plant biology. It's a profound glimpse into one of nature's most pervasive principles, scale invariance. It describes the remarkable phenomenon where an object or pattern appears statistically similar, no matter how much you magnify or shrink your view. This isn't about perfect, identical copies, but rather a consistent statistical self-similarity that repeats across different levels of observation. This mesmerizing pattern extends far beyond the forest floor. The branching network of a river delta, seen from an airplane window, bears an uncanny resemblance to the intricate branching of a tree, or even the human circulatory system. The jagged, rough silhouette of a mountain range maintains its characteristic roughness whether you're looking at a single rocky outcrop or an entire continental chain from space. And in perhaps the most grand example, the distribution of galaxies throughout the cosmos isn't random. They cluster into vast filaments and immense voids, creating a cosmic web that, when mapped, looks startlingly similar to the neural networks of a brain or the frothy structure of a soap bubble. These parallels aren't mere coincidences. They strongly suggest that diverse natural processes, from water erosion and biological growth to gravitational collapse, might all be governed by a common set of universal, scale-independent rules. The pioneering mind who gave us the mathematical language to describe this hidden order was the polymath Benoit Mandelbrot. He coined the term fractal to describe these infinitely complex shapes that are built from repeating patterns. Mandelbrot's revolutionary insight was showing that incredibly complex, organic-looking forms, coastlines, clouds, trees, could be generated by astonishingly simple iterative equations. His most famous creation, the Mandelbrot Set, is generated by a single, straightforward formula. Yet, within its boundary lies an infinite universe of detail. Zoom into any part of it, and you discover ever smaller variations of the original shape. a world within worlds that never ends. This wasn't just abstract math. It was a key to decoding the apparent chaos of the natural world. This concept of scale invariance helps explain efficiency and optimization across countless systems. Our bodies are filled with fractals. The branching structure of our lungs maximizes surface area for gas exchange within the limited volume of our chest cavity. Our circulatory system uses a fractal network of arteries, veins, and capillaries to efficiently deliver oxygen to every single cell. This design principle minimizes the energy required for distribution, a pattern that evolution has arrived at again and again. Even the electrical activity of the heart and the firing of neurons in the brain exhibit fractal-like patterns in their timing, suggesting that this isn't just about static structure, but about the very dynamics of life itself. Ultimately, the widespread presence of scale invariance hints at a deep, underlying order within what we often perceive as nature's chaos. It suggests that complexity doesn't always require complex rules. Often, simple processes repeated over and over can give rise to the rich, intricate tapestry of our reality. Understanding this concept is like finding a master key. It unlocks hidden symmetries and provides a powerful framework for seeing connections between the microscopic and the macroscopic, revealing that the universe might just be operating from a single, elegant, and deeply recursive blueprint. Picture a single snowflake tumbling silently from the winter sky. On its own, it's a masterpiece of symmetry, but look closer and you'll see its true magic. Each of its 6 delicate arms is not a smooth, solid form, but is itself decorated with an intricate lacework of smaller, perfectly identical icy patterns. Zoom in even further with a microscope, and that pattern repeats again. A breathtaking example of a natural fractal where the same beautiful design echoes down through multiple scales, all emerging from the simple, repetitive process of water molecules arranging themselves into crystals under specific atmospheric conditions. This isn't an isolated marvel. Step into a garden and you might find a stunning example in the form of Romanesco broccoli. This vegetable looks almost otherworldly, with its chartreuse color and its surface composed of countless smaller cones. Each of these cones is a near-perfect miniature replica of the entire head, and those smaller cones are themselves made of even smaller, identical spiraling buds. This isn't a random mutation. It's a precise, mathematical phenomenon in plant development known as meristematic growth, where a simple genetic algorithm instructs the plant to repeat a logarithmic spiral pattern over and over again. The result is a natural sculpture that beautifully illustrates how complex, mesmerizing forms can arise from the iteration of a basic rule. Now, pull the camera back, way back. Shift your gaze from the microscopic and the botanical to the grandest canvas of all, the cosmos. When astronomers map the universe on its largest scales, they don't find a random sprinkling of galaxies. Instead, they reveal an immense cosmic web, a vast network where galaxies cluster into long, winding filaments and immense, empty voids. This structure, when visualized, bears a striking and uncanny resemblance to other fractal networks we see in nature. The branching pattern of a lightning bolt frozen in the sky, the interconnected neurons in a human brain, or even the mycelial networks of fungi spreading through soil. The universe, at its grandest scale, appears to be organized in a way that feels intimately familiar. These profound repetitions across such wildly different domains are far more than just a visual coincidence. They point toward deep, universal principles at work. One of the most powerful is the drive for energy minimization and efficiency. Nature is a master of doing the most with the least. A river network organizes into a branching fractal pattern because that is the most efficient way to move water from a large area to a single point, minimizing the total work done by erosion over time. Similarly, our circulatory and respiratory systems are fractal because that design maximizes surface area for exchange within a limited volume, an evolutionary solution that optimizes function. This principle of self-organization, where local interactions between simple components give rise to large-scale, complex order, is what ties the snowflake to the galaxy. The intricate crystal forms from local water molecules following basic rules of attraction. The cosmic web forms from the relentless pull of gravity acting on dark matter over billions of years, where tiny initial fluctuations in density were amplified into the vast structures we see today. In both cases, a simple force applied universally and repetitively creates a complex and scalable pattern. By studying these patterns, scientists are uncovering a shared language of the universe. Climatologists use fractal mathematics to model the complex, swirling patterns of storms and cloud formations. Neuroscientists analyze the fractal nature of brainwaves to understand consciousness and diagnose neurological disorders. And cosmologists run immense computer simulations, applying these same principles of self-organization and scaling to understand how the faint echoes of the Big Bang evolved into the glittering, structured universe we inhabit today. Each of these fields is discovering that the universe seems to reuse its most effective and elegant designs, painting with the same brushstrokes from the infinitesimally small to the astronomically large. Recall the elegant spiral of a nautilus shell, a curve so perfectly formed it seems almost too beautiful to be an accident of nature. This iconic shape grows according to a precise mathematical rule, each new chamber expanding in a progression known as the Fibonacci sequence. In this simple series, each number is the sum of the two before it, 0, 1, 1, 2, 3, 5, 8, and so on, stretching into infinity. As these numbers grow larger, the ratio between successive terms gets closer and closer to an irrational number approximately equal to 1.618. This is the golden ratio, often denoted by the Greek letter phi, and it represents a proportion considered aesthetically ideal for millennia. This seemingly magical number shows up in the most unexpected places. In the world of art and architecture, it's found in the proportions of the Parthenon in Athens and the pyramids of Giza. It's embedded in the composition of Leonardo da Vinci's Vitruvian Man and the melodies of classical music. Even the human body exhibits this divine proportion, the ratio of the length of your forearm to your hand, or the spacing of your facial features, often approximates phi. For ancient thinkers like the Greek philosopher Pythagoras and his followers, this wasn't a coincidence. They saw the golden ratio as tangible proof of a hidden cosmic order, a sacred geometry that the universe used as a fundamental building block. But the story doesn't end on Earth. Lift your eyes to the heavens, and the golden ratio appears there too. The spiral arms of many galaxies, including our own Milky Way, often unfurl at an angle that aligns with this special ratio. Our solar system itself holds fascinating harmonic resonances. The orbital periods of planets sometimes relate to one another in ways that echo these mathematical principles, creating a kind of celestial music based on the same ratios that govern a nautilus shell. This profound repetition from the infinitesimally small to the astronomically vast suggests that phi might be more than just a numerical curiosity. It could be a fundamental constant woven into the very fabric of spacetime. Modern physicists are actively exploring this tantalizing possibility. In the strange world of quantum mechanics, the golden ratio has been observed in the energy levels of certain atoms and the magnetic properties of special crystals. Some researchers in string theory are investigating whether phi might play a role in the way the theory's extra dimensions compactify, determining the very laws of physics we experience. Even in the realm of general relativity and cosmology, the ratio appears in equations describing black holes and the large-scale structure of the universe. Its persistent emergence across such a dizzying array of disciplines from biology and art to quantum physics and cosmology hints at a universal language written in mathematics, with the golden ratio acting as a frequently used word or phrase. This leads us to a captivating and profound question. Could this ratio be a literal key, a piece of the code used to write the universe's operating system? Is the appearance of phi in everything from a seashell to a spiral galaxy a glimpse into a deeper, more fundamental blueprint? One where efficiency, beauty, and mathematical harmony are not human inventions but intrinsic properties of reality itself. The quest to answer this question continues to drive scientific inquiry, blurring the lines between mathematics, science, and philosophy in our enduring search to understand the cosmos and our place within its elegant, and perhaps golden, design. Now, let's shift our focus from the natural world to the abstract realm of mathematics and physics, where the idea of self-similarity takes on an even more profound and powerful meaning. The journey begins with one of the most famous mathematical objects ever discovered, the Mandelbrot Set. Generated by an almost deceptively simple formula, this intricate shape is a universe of infinite complexity contained within a finite boundary. As you zoom into its elaborate, swirling edges, you don't find chaos or randomness. Instead, you discover an endless procession of ever smaller, slightly distorted copies of the original set. It's a place where the whole is faithfully mirrored in its parts, no matter how deep you dive. This isn't just a mathematical curiosity. It's a stunning demonstration of how a basic, iterative rule can give birth to boundless, intricate beauty and order. It serves as a pure, digital testament to the principle that a universe of detail can be encoded within a single, elegant idea. This concept of scaling and self-similarity isn't confined to the world of abstract math. It's a crucial tool in the physicist's toolkit. Take, for example, the powerful framework known as renormalization group theory. This approach is essential for understanding what are called phase transitions, the dramatic moments when matter transforms from one state to another, like a magnet losing its magnetism as it heats up or water beginning to boil. At the precise critical point of this transition, something remarkable happens. The system becomes scale invariant. If you were to look at a snapshot of the swirling patterns in a pot of water just as it begins to boil, you wouldn't be able to tell if you were looking at a centimeter of water or a meter of it. The patterns of the bubbles and the fluctuations look exactly the same. Renormalization group theory provides the mathematical machinery to navigate this scale-free zone, allowing physicists to understand how the behavior of individual atoms scales up to create the properties we see in the world around us. It reveals that the blur of activity at a microscopic level gives rise to the sharp, defining changes we witness on a human scale. The pursuit of this scaling principle leads us to the very edges of theoretical physics, into territories like string theory. Here, the quest is to unify all the fundamental forces of nature, and the mathematics often points to a reality with more than the three spatial dimensions we experience. A compelling idea is that these extra dimensions aren't vast and expansive like our own. Instead, they might be curled up into an unimaginably tiny, complex space. And the shape of this space, the way these dimensions fold in upon themselves, could very well exhibit a fractal-like, self-similar structure. This suggests a breathtaking possibility that the very laws of physics we are trying to discover might themselves be scale invariant. The rules governing the interactions of strings at the tiniest conceivable scales could be directly reflected in the laws that orchestrate the dance of galaxies. This powerful lens of self-similarity provides scientists with a profound strategy for tackling the universe's most complex problems. When faced with a system that is overwhelmingly complicated, from the turbulent flow of a hurricane to the entangled quantum states of countless particles, they can search for repeating patterns across scales. By identifying these patterns, they can effectively simplify the problem, stripping away the irrelevant details to reveal the core, scalable principles at work. This approach connects phenomena that once seemed entirely separate, drawing a line from the behavior of a single subatomic particle to the grand, evolutionary history of the entire cosmos. Ultimately, this isn't just a collection of clever tricks. It points toward a deeper, more harmonious vision of nature. The recurring appearance of these mathematical patterns, from the infinite depths of a fractal to the critical point of a physical transition, hints that the universe might be speaking a single, unified language. It is a language where complexity emerges from simplicity, and where the same thematic motifs are written into every chapter of reality, from the very smallest to the very largest. This mathematical harmony is perhaps our strongest clue that a single, elegant, and unified description of nature is not just a dream, but a destination. Now let's venture into one of the most mind-bending connections of all, where the blurry, uncertain world of the impossibly small seems to directly influence the grand architecture of the entire cosmos. Picture an electron orbiting the nucleus of an atom. In our everyday experience, we imagine it like a tiny planet circling a sun, but that comforting image is shattered by quantum mechanics. The electron doesn't exist in one specific place at one time. Instead, it's described by a probability cloud, a wave of potentiality where it could be almost anywhere. This inherent fuzziness isn't a limitation of our instruments. It's a fundamental property of reality at the quantum scale. The universe, it seems, operates on a foundation of probabilities rather than certainties. Astoundingly, this quantum fuzziness finds a bizarre echo on the largest scales we can observe. For decades, astronomers have been puzzled by the way galaxies rotate. They move so fast that they should fly apart, but something invisible, something we call dark matter, holds them together with its gravitational grip. We can't see dark matter, but we can map its distribution by watching how it bends light and influences the motion of stars. What we find is that it forms vast, diffuse halos around galaxies and even larger, web-like structures connecting galaxy clusters. And just like the electron's probability cloud, the distribution of dark matter isn't sharp and defined, it's probabilistic. We can say where it's likely to be most dense, but we cannot pinpoint it with absolute certainty. It's as if the probabilistic rulebook of the quantum world has been scaled up to a cosmic level, governing the invisible scaffolding of the universe itself. This mirroring goes even deeper. The universe wasn't born smooth and uniform. The cosmic microwave background, the faint afterglow of the Big Bang, shows tiny, microscopic fluctuations in temperature ripples in the fabric of spacetime. These ripples are believed to be quantum fluctuations, tiny probabilistic jitters that were frozen in place and magnified to an astronomical scale during a period of rapid inflation in the universe's first moments. These primordial wrinkles were the seeds of all structure. Over billions of years, gravity acted on these slight overdensities, pulling in more and more matter. The result is the magnificent cosmic web we see today. A vast, fractal-like network of galaxy-rich filaments stretching across incomprehensible voids, with brilliant clusters forming at the intersections. The very largest structures in the universe appear to be a direct, amplified consequence of the very smallest quantum events. The ghostly hand of quantum mechanics, once confined to the atomic realm, seems to have written its signature across the heavens. This radical connection between scales has given rise to some of physics' most provocative ideas, like the holographic principle. This theory suggests a reality so strange it challenges our basic understanding of space and dimension. It proposes that all the information contained within a three-dimensional volume of space, everything you would need to describe every star, every planet, every atom within a black hole, for instance, can be entirely encoded on its two-dimensional boundary, its surface area. It's analogous to how a hologram works. A flat, two-dimensional film can project a fully three-dimensional image. In this view, our rich, three-dimensional reality might be a projection from a two-dimensional surface at the edge of the universe. This breathtaking idea fundamentally blurs the line between the small and the large, suggesting that depth and volume themselves might be emergent properties arising from a more fundamental, flat reality. What these parallels suggest is nothing short of revolutionary. Quantum mechanics, which governs the world of particles, and cosmology, which describes the universe as a whole, may not be separate domains at all. They might be two different expressions, two different viewpoints, of the same underlying set of principles. The rules that dictate how a particle behaves might be the same rules, scaled up, that dictate how a galaxy cluster forms. This connection is an open invitation, a compelling call to explore how the spooky, probabilistic dance of the very small directly shapes and defines the majestic, gravitational ballet of the very large, weaving a single, unified tapestry from the quantum foam to the cosmic web. Consider the simple, perfect symmetry of a snowflake. Rotate it by 60 degrees and it looks exactly the same. This isn't just a beautiful accident. It's a fundamental property of its underlying crystal structure, a visual hint at a principle that runs far deeper than frozen water vapor. This idea of symmetry, where an object or a system remains unchanged under a specific transformation, like rotation or reflection, isn't just a geometric curiosity. It is, in many ways, the very engine of the universe, dictating the most fundamental laws that govern everything from the motion of planets to the interactions of the smallest particles. This profound connection between symmetry and physical law was crystallized in one of the most beautiful theorems in all of physics, developed by the mathematician Emmy Noether. She discovered that for every continuous symmetry in nature, there is a corresponding conservation law. This is a breathtakingly powerful idea. The fact that the laws of physics don't change from one moment to the next, a symmetry in time, directly leads to the conservation of energy. The fact that the laws of physics are the same in every location, a symmetry in space, leads to the conservation of momentum, and the fact that the laws don't change depending on the direction you're facing, rotational symmetry, gives us the conservation of angular momentum. So the very reason that energy cannot be created or destroyed, but only transformed, is rooted in this deep, temporal symmetry of the cosmos. The universe's unwavering consistency guarantees its most fundamental balances. Dive into the quantum realm, and symmetry takes on an even more central, albeit more abstract, role. The entire standard model of particle physics, our most successful framework for describing the fundamental constituents of matter and their interactions, is built upon a concept known as gauge symmetry. This is a kind of internal symmetry, a freedom to change how we describe a particle's field in a certain way at every point in space-time, without affecting any observable outcome. It might sound esoteric, but this requirement for local symmetry is what actually creates the fundamental forces themselves. The symmetry associated with the electromagnetic force necessitates the existence of the photon, the particle that carries that force. The symmetries of the strong and weak nuclear forces demand the existence of gluons and the W and Z bosons. In this breathtakingly elegant framework, the forces of nature aren't just governed by symmetry, they are born from it. The particles we see and the forces they feel are the inevitable consequence of the universe's demand for symmetry. Yet if the universe were perfectly symmetrical, it would be a very boring place. A state of perfect, featureless uniformity. The incredible richness and diversity we see all around us, from the different elements to the galaxies and life itself, arise from a phenomenon known as broken symmetry. Think of a phase transition like water cooling into ice. The liquid water is highly symmetric. It looks the same in every direction, but as it freezes, it crystallizes into a specific, structured lattice. It has chosen an orientation, breaking the full rotational symmetry of the liquid state, to settle into a new, lower energy state with a different, more restricted symmetry. This breaking is what gives the ice its definite structure. This process of symmetry breaking is a cosmic creative force. In the earliest moments of the universe, a single, unified force may have existed in a state of perfect symmetry. As the cosmos expanded and cooled, this symmetry broke, fracturing into the four distinct forces we recognize today: gravity, electromagnetism, and the strong and weak nuclear forces. This primordial breaking set the stage for everything to come. Even the formation of galaxies can be seen as a result of broken symmetry. The initial universe was almost perfectly smooth, but tiny quantum fluctuations broke that uniformity. Gravity then amplified these tiny asymmetries, pulling matter into the magnificent, structured cosmic web of clusters and voids we observe today. In our technology, superconductors work because of a broken symmetry that allows electrons to pair up and flow without resistance. This beautiful interplay between a pristine, symmetrical initial state and the subsequent breaking that introduces complexity is what weaves the rich and varied tapestry of reality. This leads physicists to a compelling and profound hypothesis: that the ultimate blueprint of the universe might be written in the language of symmetry groups, the mathematical structures that describe these invariances. The quest for a theory of everything, a single framework that unifies all forces and particles, is largely a search for a master symmetry from which all others emerge. It is the pursuit of a primordial, perfect symmetry that existed at the birth of the cosmos, whose breaking and fragmentation generated the dazzling diversity of the physical world, from the whirl of galaxies to the bonds between atoms. To unravel these symmetries is to perhaps finally read the cosmic code in its original, uncorrupted form. Watch a double pendulum, that mesmerizing contraption of two arms connected by a hinge, and you'll witness chaos in its purest form. Give it a gentle push, and it might swing in a lazy, predictable arc. But nudge it just a fraction differently, and its motion becomes a wild, unpredictable flail, each swing seemingly divorced from the last. This is the famous butterfly effect. In action, the core principle of chaos theory, where infinitesimally small differences in the starting conditions can lead to dramatically divergent outcomes over time. It's a powerful demonstration that in complex systems, perfect prediction can be impossible, not because of a lack of laws, but because we can never know the initial state with infinite precision. Yet, within this apparent pandemonium, a hidden order resides. If you were to map the chaotic swings of that double pendulum in a special mathematical space called phase space, plotting its position against its momentum, you wouldn't see a random scribble. Instead, a beautiful, intricate structure would emerge, known as a strange attractor. This isn't an attractor in the physical sense, but a fractal pattern that defines the boundaries within which the system can operate. No matter how chaotic the motion seems, the pendulum's behavior is forever bound to trace this intricate, invisible template. It's a profound revelation. Even in the heart of chaos, there is a deep, underlying architecture, a deterministic pattern that guides the madness. We see this delicate dance between chaos and order play out all around us. Our weather is a classic example of a chaotic system. Meteorologists use incredibly sophisticated models, but long-term forecasting remains a formidable challenge because the atmosphere is so exquisitely sensitive to initial conditions. A tiny change in ocean temperature or wind direction, thousands of miles away, can alter the path of a hurricane or determine whether a week will be rainy or dry. Yet within this chaos, we also see repeating, large-scale patterns emerge over time, like the jet stream or El Niño cycles. The system is deterministic. It follows the strict laws of fluid dynamics and thermodynamics, but its complexity makes it unpredictable, weaving a tapestry of order from threads of chaos. This principle extends far beyond our planet. Our solar system, often thought of as a perfect clockwork mechanism, also contains pockets of chaos. The orbits of asteroids, for instance, can be influenced by the gravitational tugs of planets in ways that are incredibly difficult to forecast over millions of years. On a grander cosmological scale, many scientists believe the initial conditions of the Big Bang itself were set by a kind of quantum chaos, tiny, random fluctuations in a primordial field. These minuscule, chaotic seeds were then stretched across the cosmos during inflation, becoming the gravitational wells that eventually attracted matter to form the first galaxies, stars, and planets. In a very real sense, the entire large-scale structure of our universe, the magnificent cosmic web with its great walls and vast voids, may be the frozen echo of that initial cosmic chaos. What chaos theory ultimately teaches us is that randomness and determinism are not opposites. They are two sides of the same coin. A system can be entirely governed by fixed, unbreakable laws, and yet produce behavior that is for all practical purposes unpredictable and rich with novelty. This is the engine of creativity in the universe. It is why complex systems, from swirling storm clouds to evolving ecosystems, don't just descend into noise. Instead, they often self-organize, giving rise to the scalable, fractal patterns we see in coastlines, mountain ranges, and galactic clusters. This beautiful duality, the marriage of unpredictable freedom and deeply structured order, is not a flaw in the universe's design. It may be its most fundamental feature, the very mechanism that allows for both the stability of physical law and the stunning diversity of the cosmos. Now, let's pull back and look at the universe through a different lens, not as a collection of separate objects, but as an immense and interconnected web of relationships. Consider the Internet, that global tapestry of computers and cables. It's not a random mess. It's a highly organized network where certain major hubs, like massive data centers, have an enormous number of connections, while your home router has just a few. This structure isn't unique to our technology. Zoom into the human brain, and you'll see a strikingly similar architecture. Billions of neurons, with a relatively small number of highly connected hub neurons that play a crucial role in efficiently shuttling information across different regions. Now, pull the camera back to the farthest reaches of space. The cosmic web of galaxies, connected by faint filaments of dark matter and gas, forms a network that, when mapped, looks astonishingly like a neural network or the Internet. These three systems, technological, biological, and cosmological, exist on vastly different scales, yet they all share profound organizational similarities. Scientists describe these shared properties with terms like small world connectivity and scale-free distributions. Small world connectivity means that you can get from any one node to any other in a surprisingly small number of steps, which is why you can often connect to any person on Earth through just a handful of acquaintances, or why information can travel across the global Internet in milliseconds. A scale-free distribution describes the way connections are spread out. In these networks, most nodes have very few links, but a few nodes become incredibly well-connected hubs. This pattern isn't a coincidence. It emerges from a simple, powerful rule often called preferential attachment. In essence, new nodes entering the network tend to link up with the nodes that are already the most popular and well-connected. It's a classic case of the rich getting richer. A new website is more likely to link to Google than to a tiny, unknown blog. A new neuron is more likely to form connections with already well-integrated neurons. This simple rule creates robust, efficient, and hierarchical structures that repeat from our social circles to the organization of proteins within a cell. This framework of network theory gives us a universal toolkit for decoding complexity. In the world of physics, the interactions of subatomic particles are depicted using Feynman diagrams. These aren't literal pictures but are essentially network maps, with lines representing particles and vertices representing their interactions, collisions, absorptions, and emissions. These diagrams map the hidden network of the quantum world, In astronomy, we don't just see galaxies as isolated islands. We see them as nodes connected by the gravitational bridges of dark matter filaments. These invisible threads form the literal scaffolding of the universe, a grand network upon which visible matter is draped. Ecologists use network theory to map food webs, showing how the loss of one key species, a hub, can cause a cascade of failure through an entire ecosystem. What this reveals is a breathtakingly simple idea. Complexity often arises from simplicity. Seemingly intricate and intelligent designs, our brain, the internet, the universe, can self-organize from a few basic, iterative rules. There's no grand architect meticulously drawing each neural connection or galactic filament. Instead, these vast, complex networks emerge naturally from local interactions. This points toward a common architectural plan, a universal set of blueprints for building stable, efficient, and resilient systems of connections, regardless of whether the nodes are people, web servers, neurons, or galaxies. The universe appears to have a preferred way of linking things together, and network theory is the key we're using to decipher that deeply embedded code. Marvel for a moment at the humble tree standing outside your window. Its trunk rises from the ground, splitting into sturdy branches, which then divide into smaller twigs, and finally into a delicate network of leaves and veins. This isn't a random design. It's a masterpiece of natural engineering, a fractal branching system perfected over millions of years to do one thing with supreme efficiency: distribute resources. The tree's structure is optimized to pull water and nutrients from its roots up to its highest leaves with the least possible resistance, maximizing its exposure to sunlight and air. Now cast your gaze much, much higher. The cosmos presents a structure of startling similarity: the cosmic web, vast filaments of dark matter, the invisible scaffolding of the universe, channel gas and dust between immense galaxy clusters. These cosmic rivers of matter are not smooth highways. They are themselves complex, branching networks, the largest structures in the known universe. And they obey a similar drive for efficiency, governed by gravity's relentless pull to create the most probable, least energy-intensive paths for matter to flow. From the microscopic veins on a leaf to the gargantuan bridges between galaxies, nature seems to have a preferred blueprint for building distribution networks, and it is written in the language of fractals. This is more than a visual coincidence, it's a deep physical principle. In biology, this optimization is described by Murray's law, which mathematically explains the diameters of branching tubes in circulatory and respiratory systems to minimize the energy required for pumping blood or air. The human body is a walking testament to this. Our lungs are a fractal wonder. The trachea branches into the bronchi, which branch again and again into nearly 500 million tiny alveoli. This design creates an immense surface area roughly the size of a tennis court, crammed into your chest, all to maximize the efficiency of gas exchange. Astoundingly, physicists see echoes of this same branching efficiency in the large-scale structure of the universe, where the gravitational pumping of matter along filaments follows analogous rules to minimize energy expenditure. The universe, it seems, reuses its most effective designs. The parallels become even more profound when we push the boundaries of scale. Consider the human lung once more. Its intricate, fractal architecture is not just for efficiency. It creates a complex, undulating surface. Now, venture down to the quantum realm, to the very foam-like texture of spacetime itself. Theoretical models suggest that at the Planck scale, spacetime is not smooth and continuous, but is a seething, dynamic froth of virtual particles popping in and out of existence. This quantum foam is often described as having a fractal geometry, a turbulent, complex structure that defies classical geometry. While separated by over 35 orders of magnitude, the branching, air-filled labyrinth of the lung and the frothy, energetic foam of the quantum vacuum both exhibit a similar organizational complexity. It's as if the same chaotic, creative turbulence is expressed in the shape of an organ that gives us life, and the very fabric of the reality that contains us. Some researchers are exploring parallels that are even more speculative, yet utterly captivating. Take the iconic double helix structure of DNA, the molecule that carries the genetic instructions for all known life. Its elegant, twisted ladder form is a symbol of biology itself. Now, look out into the disk of a spiral galaxy. As galaxies rotate, their immense magnetic fields can be stretched and twisted by the differential rotation of stellar material. This process can generate vast, helical magnetic fields that spiral through the galactic arms, channels that can influence star formation and the flow of cosmic rays. While the forces at play are entirely different hydrogen bonds and van der Waals forces in one, gravity and magnetohydrodynamics in the other, the emergence of a helical, information-carrying structure in both a biological and an astronomical context is a pattern that invites wonder. It suggests that certain forms may be fundamental solutions to problems of organization and stability, whether you're building a molecule or a galaxy. What do these breathtaking echoes mean? They suggest that life is not an isolated phenomenon separate from the cold mechanics of the cosmos. Instead, life might be understood as an intense, localized expression of the very same universal patterns and physical laws that shape galaxies and quantum fields. Evolution did not have to invent efficient branching or stable helical structures from nothing. It worked with a pre-existing toolkit, sculpting biology within a framework of physical principles that favor certain forms for certain functions. The universe has a tendency toward patterns that are efficient, resilient, and scalable. Life, in its magnificent complexity, appears to be playing variations on these deepest of cosmic themes, evolving within a universe that already hums with a latent order waiting to be expressed. To explore these biological cosmic parallels is to profoundly deepen our appreciation for the unity of nature, seeing our own existence not as separate from the cosmos, but as a conscious, breathing part of its magnificent, patterned whole. Ponder for a moment the number pi. It's one of the first mathematical constants we learn, the ratio of a circle's circumference to its diameter, approximately 3.14159. But its reach is far more profound than geometry class. Pi appears in the fundamental description of an electron's orbital around an atomic nucleus, a wave-like probability cloud that defines a spherical region of space. Zoom out to a planetary scale, and pi is there too, embedded in the equations that describe a planet's elliptical orbit around its star. This same constant, unchanging and irrational, operates with equal authority in the quantum realm and the celestial, a silent participant in the architecture of reality at wildly different scales. Then there's the fine structure constant, a number far less famous but arguably even more mysterious. Denoted by the Greek letter alpha, its value is approximately 1/137. This isn't a geometric ratio. It's a pure, dimensionless number that governs the strength of the electromagnetic force. The force that holds atoms together, dictates how light interacts with matter, and is the very reason chemistry exists. If this number were even slightly different, the consequences would be cosmic. A stronger electromagnetic force would bind electrons so tightly to atomic nuclei that chemical reactions and the complex molecules essential for life might never form. A weaker force, and atoms couldn't hold together at all. Stars might not burn, and the universe would be a bland soup of subatomic particles. Its seemingly precise, finely tuned value has led some physicists and philosophers to wonder if it is a fundamental key without which the complex universe we inhabit simply couldn't exist. These constants are more than just numbers we plug into equations. They appear to be invariant, unchanging pillars in the universe's operating system. They act as fundamental parameters, the fixed settings upon which the laws of physics are built. Their values are not predicted by any current theory. We simply measure them through observation. Why does pi have its specific, never-ending value? Why is the fine structure constant exactly 1/137, and not some other number? We don't know. They are the givens, the starting points, and their persistence across such a dizzying array of phenomena suggests they are part of a deeper cosmic code, written into the fabric of everything. This idea becomes even more compelling when we look at the frontiers of theoretical physics, such as string theory. This ambitious framework proposes that the fundamental constituents of the universe are not point-like particles but tiny, vibrating strings. For the math of this theory to work, it requires the existence of extra-spatial dimensions far more than the three we experience. But we don't perceive these dimensions because they are compactified, curled up into an unimaginably small, complex shape. And here's the crucial part. The precise way these dimensions are folded is determined by mathematical constants. The specific geometry of this hidden, compact space then dictates the properties of the particles and forces we see in our everyday world. The mass of an electron, the charge of a quark, the very strength of the forces themselves. In this view, the constants we measure are the direct consequence of the hidden geometry of the universe, a geometry defined by these immutable numbers. The evidence for this coded reality is all around us, woven into the patterns of nature. The same golden ratio that defines the spiral of a nautilus shell often appears in the logarithmic spirals of galaxies. The vibrations of molecules and the resonant frequencies of stars can be described using the same mathematical constants that govern the behavior of subatomic particles. This isn't just a happy coincidence. It's a powerful hint that the universe speaks a consistent mathematical language. The constants are the universal nouns and verbs of that language, appearing in every chapter, from the microscopic to the cosmic. This leads us to one of the most profound questions in all of science. Why do these constants have the specific values that they do? Is it a random accident, a frozen roll of the dice in the first moments of the Big Bang? Or is it a necessary output of a deeper, yet-to-be-discovered theory? A final equation that would reveal these values not as arbitrary inputs, but as inevitable results. Deciphering this code, understanding the origin of these numbers, is perhaps the ultimate goal of physics. It wouldn't just complete our textbook equations, it would reveal the deepest secrets of reality itself, allowing us to read from the universe's original, fundamental blueprint. To understand how the universe grew from a microscopic speck into the vast cosmos we see today, we need to journey back to its very first moments, to a period of almost unimaginable transformation. In the tiniest fraction of a second after the Big Bang, the entire observable universe is thought to have undergone a breathtaking growth spurt known as inflation. This wasn't a gentle expansion. It was a violent, exponential stretching of spacetime itself, doubling in size over and over again in intervals so short they are almost impossible to comprehend. What could possibly power such a monumental event? The leading theory points to a mysterious entity known as a scalar field, often called the inflaton field. Imagine this as a kind of energy field that temporarily possessed a very unusual property. It created a powerful repulsive gravity, acting like an anti-gravity force that pushed every point in the universe apart from every other point at a ferocious rate. This incredible surge of expansion performed two absolutely critical jobs for the cosmos. First, it ironed out the universe, smoothing any initial wrinkles or irregularities to create the stunningly uniform large-scale structure we observe. Second, and perhaps even more remarkably, it took the faintest whispers of quantum noise and stretched them across the cosmos, planting the seeds for all future structure. This process of inflation left behind a permanent, frozen record of its activity, And it's a record that beautifully demonstrates the concept of self-similarity across scales. The quantum fluctuations that flickered in and out of existence during that primordial era were not smoothed away by the inflation. Instead, they were magnified to astronomical sizes. These tiny, random variations in the density of the inflated field were stretched into colossal ripples in the fabric of spacetime. These ripples, imprinted as faint temperature variations in the afterglow of the Big Bang, the cosmic microwave background, form a pattern that is statistically identical no matter how large a patch of the sky you examine. The patterns of hotter and colder spots, the seeds of future galaxies and voids, look the same whether you're looking at a region a billion light-years across or 10 billion. This scale invariance in the universe's very first light is a powerful fingerprint, a direct signature of its quantum origins blown up to a cosmic scale, directly linking the behavior of the impossibly small to the architecture of the impossibly large. The fascinating thing about scalar fields is that they aren't just a theoretical device for cosmologists. They are a well-established mathematical tool that appears in many different branches of physics, demonstrating how the same concepts apply across scales. In condensed matter physics, for instance, the behavior of superconductors is described using a scalar field. When certain materials are cooled to extremely low temperatures, they undergo a phase transition where electrical resistance suddenly drops to zero. This transition is governed by a field that, much like the inflaton, has a specific value that changes, breaking a symmetry and giving rise to the superconducting property. The mathematics used to describe the Higgs field, which gives elementary particles their mass, also relies on a scalar field. So the same type of physical entity that might be responsible for structuring the entire cosmos is also at work explaining how electrons can flow without resistance in a lab on Earth. This isn't just a happy coincidence. It highlights a profound universality in the language of physics. The mathematical tools we use to understand the birth of the universe are directly applicable to understanding exotic states of matter, suggesting that the universe's blueprint might be written in a common dialect. Inflationary cosmology, powered by this scalar field dynamics, therefore achieves something truly extraordinary. It forges a direct and tangible bridge between the two great pillars of modern physics, quantum mechanics and general relativity. It takes the fuzzy, probabilistic world of the quantum, a realm where particles flicker in and out of existence and nothing is certain, and shows how those microscopic fluctuations were amplified by gravity to become the deterministic seeds for galaxies, stars, and planets. It solves the puzzle of why the universe is so uniform while simultaneously explaining the origin of all structure within it. The inflaton field acts as the cosmic translator, converting the random grammar of quantum mechanics into the gravitational syntax that built the cosmic web. This makes the concept of a scalar field far more than just an abstract theoretical idea. It positions it as a potential key element in the universe's fundamental operating system, a versatile and powerful component of the universal blueprint that shapes reality from the subatomic to the supergalactic. Gaze up at the night sky and you're witnessing a cosmic dance of nested hierarchies, a gravitational choreography that repeats itself on every scale. The Moon is locked in orbit around the Earth, which itself sweeps in a grand elliptical path around the Sun. Our entire solar system, in turn, is just one of hundreds of billions of stars swirling around the center of the Milky Way galaxy. And the Milky Way doesn't exist in isolation. It's a major member of our local group, a gravitationally bound family of galaxies that includes the Great Andromeda Galaxy and dozens of smaller dwarfs. This entire local group is then falling toward the immense Virgo cluster, part of the even larger Laniakea supercluster. It's a profound realization. The universe is structured like a set of Russian dolls, with systems nestled within systems all the way up. This beautiful, scalable organization isn't a random accident. It's the direct and elegant consequence of gravity's inverse square law, This fundamental rule states that the force of attraction between two objects weakens with the square of the distance between them. This specific mathematical relationship is what makes stable, hierarchical structures not just possible, but inevitable. It allows for a small, close object like a moon to be tightly bound to its planet, while that entire planet-moon system can orbit a star at a much greater distance without being torn apart. The same law that keeps your feet on the ground also orchestrates the motion of galaxy clusters hundreds of millions of light-years across. Gravity is the ultimate sculptor, and its favorite form appears to be this nested, repeating architecture. We see this same hierarchical principle at work in the very birthplaces of stars. Giant molecular clouds, the vast cosmic nurseries drifting through galaxies, are not smooth, homogeneous blobs of gas. Instead, they possess a complex, clumpy, and deeply fractal structure. These clouds are riddled with dense knots and filaments, which themselves contain smaller, denser clumps. It's a pattern of turbulence and self-gravity that repeats over and over, like swirling eddies within a mighty river. Within these smallest, densest clumps, gravity finally wins its battle against internal pressure, and a protostar is born. Often, these processes don't create single stars but entire clusters of sibling stars, all forming together from the same hierarchical cloud. This means our own sun was likely born in a crowded stellar nursery alongside hundreds of other stars, all originating from this cascading fractal collapse. Because this pattern is so universal, astronomers actively use hierarchy as a powerful modeling tool to understand phenomena across the cosmos. The intricate structure of Saturn's rings, for example, isn't just a smooth sheet of ice. It's composed of countless individual particles that gather into moonlets, which are then shepherded into distinct bands and gaps by the gravitational influence of Saturn's moons, a perfect example of a hierarchical system in miniature. On the grandest scales, the distribution of the universe's most mysterious component, dark matter, is also understood through this lens. Supercomputer simulations show that dark matter doesn't just form smooth halos around galaxies, it builds up in a hierarchical fashion. Small clumps of dark matter form first, and then through countless mergers and acquisitions over billions of years, they assemble into the larger halos that host the galaxies we see. This process, known as hierarchical structure formation, is the leading model for how the entire cosmic web built itself up from the near uniformity of the Big Bang. This overwhelming evidence points to a captivating conclusion. The universe seems to build complexity not through singular, monolithic acts of creation, but through a process of repetition and self-assembly. Simple rules, applied over and over again across vast expanses of space and time, allow for the bottom-up construction of increasingly intricate and grand structures. From the tiniest moonlet to the largest supercluster, the cosmos appears to be engaged in a constant process of organization, using the same gravitational toolkit to assemble systems at every scale. This hierarchical arrangement is more than just a convenient way to classify what we see. It's a fundamental feature of a universe that constructs its magnificent order through a deeply embedded language of recurring patterns and scalable designs. Think about a single, solitary molecule of water. On its own, it's a simple trio of atoms, 2 hydrogen, 1 oxygen bouncing around according to the basic rules of chemistry and physics. It has no concept of wetness, no capacity to flow, and certainly no ability to form a crashing wave. Yet, when you gather trillions upon trillions of these simple molecules together, something miraculous happens. They cease to behave as individuals and begin to act as a collective. From their countless minute interactions, entirely new and breathtakingly complex behaviors emerge. The gentle lapping of water on a shore, the powerful, swirling chaos of a whirlpool, the majestic, rolling form of an ocean wave. This is the profound concept of emergence, where the whole becomes undeniably greater than the sum of its parts, giving rise to properties and laws that simply do not exist at a lower level. This principle is one of the most powerful ideas in all of science, providing a framework to understand how complexity births itself from simplicity. In physics, the entire field of thermodynamics, with its laws governing heat, work, and entropy, is a classic example of an emergent phenomenon. These macroscopic laws are not written into the individual quantum particles themselves. You cannot find the second law of thermodynamics in a single electron. Instead, these powerful, predictable laws emerge statistically from the frenzied, chaotic interactions of countless particles. The temperature of a gas is an emergent property of the average kinetic energy of its molecules. The pressure it exerts is an emergent result of countless tiny collisions against a surface. The laws that govern the steam engine, the refrigerator, and the star are not fundamental. They are the inevitable outcome of simpler rules playing out on a grand scale. Now, pull the camera back to the grandest stage of all, the cosmos. The majestic spiral galaxies, the brilliant clusters, and the vast, dark voids are themselves emergent phenomena. They were not simply present in the early universe like ingredients waiting to be stirred. They emerged over billions of years from the gravitational dance of dark matter. Individual particles of dark matter, governed by the simple, relentless pull of gravity, began to clump together through countless interactions. Small clumps merged into larger ones, weaving a cosmic web of filaments and nodes. This gravitational emergence provided the scaffolding upon which normal gas could coalesce, collapse, and ignite into the first stars, lighting up the structures we see today. The galaxy is not a fundamental object. It is a pattern that emerged from the bottom up, self-organizing interactions of its constituent parts. What's truly fascinating is that these emergent properties often carry the signature of self-similarity, creating a beautiful bridge between the simple and the complex. Consider a system at its critical point, like water transitioning between liquid and gas. At this precise moment, the system becomes scale invariant. The swirling patterns of droplets and vapor look the same whether you're observing a centimeter of space or a meter of it. This is emergence in its most fractal form. The complex, large-scale behavior is a direct reflection of the microscopic interactions, frozen at a point of perfect balance between order and chaos. It's a powerful demonstration that the patterns we see repeated across reality are often not top-down designs, but bottom-up emergences. This leads us to a radical and captivating suggestion about the universe's blueprint. Perhaps it is not a static, predetermined set of instructions like an architect's detailed plan. Instead, the cosmic blueprint might be more like a simple set of starter rules, the fundamental laws of physics, that, when set in motion, allow for a universe of breathtaking complexity to evolve and emerge through endless interactions. The patterns that repeat across scales, from the branching of a tree to the filament of a galaxy, may not be copies of a master template, but rather independent solutions that emerge because they are efficient, stable, and natural outcomes of the underlying rules. This view places the interplay between simplicity and complexity at the very heart of reality, suggesting that the universe's most stunning creations are not built, but born. They emerge again and again from the beautiful and relentless conversation between its simplest parts. Now, let's venture into one of the most radical and mind-bending ideas in all of physics, a concept that challenges our most basic intuitions about space, dimension, and reality itself. It begins with a paradox surrounding the most mysterious objects in the cosmos, black holes. When an object falls into a black hole, it seems to vanish completely, lost forever behind the event horizon. This presents a fundamental problem for physics because, according to quantum mechanics, information can never be truly destroyed. It might be scrambled, but it can't be erased from the universe. The brilliant work of physicist Jacob Bekenstein and later Stephen Hawking led to a stunning resolution. They discovered that a black hole's entropy, which is a measure of its hidden information content, its degree of disorder, is not proportional to the volume of the whole, as you might intuitively guess. Instead, it is precisely proportional to the surface area of its event horizon. It's as if all the information about everything that has ever fallen into that black hole, every star, every planet, every atom, is not stored in its vast, three-dimensional interior, but is somehow encoded on its two-dimensional boundary, like a cosmic fingerprint smeared across the surface of a sphere. This astonishing discovery was the seed for what is now known as the Holographic Principle. Inspired by these findings and further developed within string theory, this principle makes a claim so bold it seems like science fiction. It proposes that our entire three-dimensional universe, with all its rich depth, galaxies, stars, and people, might actually be a projection from a two-dimensional surface at the cosmic edge. Much like a hologram, where a flat, two-dimensional film can create the illusion of a full three-dimensional image, everything we see and experience might be a kind of projection. The laws of physics that operate in our voluminous world could be translated from a set of laws operating on a distant, flat boundary. This doesn't mean our reality is an illusion. It means that the information that defines our reality is stored on that lower dimensional surface. In this view, the very distinction between different scales begins to blur and break down. The very large and the very small are not separate realms. They are two different expressions of the same underlying informational reality, connected through this profound holographic correspondence. This shift in perspective is part of a much broader revolution that sees information not as a passive description of reality, but as its most fundamental currency. This isn't just a cosmological idea. It's a principle that appears in the most advanced technologies we are building today. Consider the neural networks that power modern artificial intelligence. These systems process information in a deeply scalable way, with layers of nodes and connections that can identify patterns in data, from recognizing faces in a photo to translating languages. Their structure and function are not about storing a literal picture of the world, but about efficiently encoding and processing information. Similarly, in the field of quantum computing, we use quantum bits or qubits. Unlike a classical bit that is either a 0 or a 1, a qubit can be in a superposition of both states simultaneously. This allows a quantum computer to process information in a massively parallel way, exploring countless possibilities at once. The way these systems handle information is not bound by our classical intuitions. They operate on principles of scalability and parallel processing that feel inherently cosmic, echoing the way the universe itself might be processing data on a grand scale. If we take this idea to its logical extreme, that the universe is fundamentally informational at its core, then so many of the patterns we've explored suddenly appear in a dazzling new light. Those intricate fractals, repeating from the smallest fern to the largest galaxy cluster, might not be merely geometric shapes. They could be the visible manifestations of an underlying data compression algorithm or a kind of cosmic computation. A fractal is, after all, an incredibly efficient way to store information. A simple mathematical formula can generate an infinite amount of visual complexity. The universe might be using similar principles of efficient encoding, writing the laws of physics in a language that maximizes information while minimizing fundamental computational resources. The beautiful, swirling patterns of a galaxy or the branching of a tree could be the output of nature's most elegant code. This perspective is nothing short of transformative. It suggests that what we traditionally think of as the fundamental building blocks space, time, and matter might be secondary, emergent properties. The true bedrock of reality could be bits of information, and the laws of physics could be the software that governs how that information is processed and displayed. We are no longer just living in a universe of things. We are living in a universe of information. a vast, dynamic computation whose output is the breathtaking, patterned reality we experience every day. It is a shift that places the concept of information at the very center of our quest to understand the cosmos, suggesting that to decode the universe's blueprint, we must first learn to read its code. Look around and you'll see that the universe is not just patterned in space, but in time as well. A pendulum swings back and forth with metronomic regularity. A planet completes its annual journey around its star, and the seasons shift in an endless, dependable loop. These are cycles, the rhythmic heartbeats of reality, and they echo across every scale of existence. But this isn't just about simple repetition. These temporal patterns often hold within them a deeper, more complex structure, one that hints at a universe where time itself is woven with repeating, scalable motifs. Consider the incredible life cycle of a star. A massive star is born from a collapsing cloud of gas. It burns brightly for millions of years through nuclear fusion, and then it dies in a spectacular supernova explosion, scattering its enriched remains across space. Those very remnants then become the raw material for a new generation of stars and planets. This isn't a linear process. It's a great cosmic cycle of birth, death, and rebirth, a loop that has been turning for billions of years, gradually populating the universe with the heavy elements necessary for planets and even life itself. Some cosmological theories, like the conformal cyclic cosmology proposed by physicist Roger Penrose, take this idea to its ultimate extreme. They suggest that our universe might not be a one-time event, but part of an endless series. In this model, the far, far future of our expanding, fading universe could become mathematically identical to the high-energy Big Bang of a new one, creating an eternal cycle of cosmic inflation and contraction. What's truly fascinating is that these cycles in time often exhibit the same kind of complex, fractal-like behavior we see in spatial structures. They aren't always perfectly regular clocks. Take the human heartbeat. A healthy heart doesn't beat with the monotonous tick of a metronome. Its rhythm has subtle, complex variations. If you analyze the timing between beats over a long period, you discover a fractal pattern variations within variations that are statistically self-similar across different time scales. This is a sign of a healthy, adaptive system. Similarly, Earth's climate operates on cycles, from the daily weather to the ice ages that come and go over tens of thousands of years. Within these large cycles are nested smaller ones, like the El Niño Southern Oscillation, which itself can show period doubling routes to chaos, a process where a cycle suddenly doubles its period, becoming increasingly complex and unpredictable, a hallmark of chaotic systems that creates a fractal structure in time. This concept of resonance provides a powerful link between the cycles of the very small and the very large. In the quantum world, atoms don't just passively exist. They can absorb and emit energy. But they are very choosy about it. They only interact with light at very specific, precise frequencies that correspond to the differences between their electron energy levels. This creates a unique atomic spectrum for each element, a fingerprint of light that is a direct manifestation of the atom's internal cyclical rhythms. Now, leap to a scale of unimaginable power, the collision of two black holes. As these monstrous objects spiral inward toward their final merger, they ripple the fabric of spacetime itself, sending out gravitational waves. The frequency of these waves increases in a specific pattern as the black holes get closer and closer, and this pattern contains a wealth of information about their masses and spins. Just like an atom, this massive system has its own resonant frequencies, its own signature song written in the vibrations of spacetime. The fact that both an atom and a pair of black holes exhibit these resonant frequencies suggests that the universe uses a common language of cyclical vibrations across all scales. This pervasive recurrence of cycles, from the biochemical reactions that power our cells to the orbital motions that define solar systems, points toward a profound idea. Time might not be a featureless linear arrow. It may be an integral, structured part of the universe's blueprint, possessing its own set of repeating, scalable patterns. The laws of physics seem to naturally give rise to oscillatory behavior, to feedback loops and rhythms that create a complex tapestry of temporal order. Understanding these patterns is more than an academic exercise. It could be the key to unlocking predictions about the future of complex systems, from forecasting the long-term changes in our climate to perhaps, one day, understanding the ultimate fate of the cosmos itself. The universe may not only be built on repeating shapes, but on repeating rhythms, a symphony of cycles playing out across every dimension of time. Imagine a team of aerospace engineers designing a new jet. They don't build a full-sized billion-dollar prototype for their first test. Instead, they craft a perfectly scaled-down model and place it inside a wind tunnel. But here's the crucial part. They don't just make it smaller. They carefully adjust the conditions of the test, the density of the air, the speed of the flow, to match a special, dimensionless number called the Reynolds number. This number, which represents the ratio of inertial forces to viscous forces in a fluid, is the master key. When the Reynolds number is the same, the behavior of the air flowing around the tiny model will be dynamically similar to how it would behave around the full-sized aircraft. The swirling vortices that form behind the wings, the patterns of laminar and turbulent flow, all of it scales. This powerful technique of scale modeling relies on a fundamental truth. The laws of physics don't care about absolute size, only about the relationships between forces. If you can preserve the key ratios, you can make a tiny laboratory experiment faithfully mimic a massive real-world phenomenon. This engineering marvel is a practical application of a much deeper and more profound scientific principle known as dimensional analysis. At its heart, this is the study of the units we use to measure the universe: mass, length, time, charge, and so on. Physicists discovered that any physically meaningful equation must be dimensionally consistent. The units on one side must match the units on the other. This simple rule is surprisingly powerful. It allows scientists to deduce how different physical quantities must be related to each other, often revealing elegant relationships that hold true across staggering differences in scale. By constructing dimensionless constants, pure numbers that have no units because all the dimensions cancel out, we can compare the fundamental strengths of nature's forces in a way that is independent of any specific scale or system. These constants become the universal invariants, the true benchmarks of reality. Consider one of the most famous dimensionless constants, the fine structure constant we discussed earlier, approximately 1/137. This number defines the strength of the electromagnetic force, but we can also create a similar constant for gravity. Imagine calculating the ratio of the gravitational force to the electromagnetic force between two protons. The result is an unimaginably tiny number, something like 10 to the negative 36. This number is so small because gravity is incredibly weak compared to electromagnetism. But here's the extraordinary part. This specific ratio, this pure number, might play a decisive role in shaping the structure of reality at both ends of the scale. In the molecular world, it's why gravity is completely irrelevant. Chemical bonds and the structure of materials are entirely dominated by the electromagnetic force. But zoom out to an astronomical scale, and the equation flips. The immense collective mass of stars and gas makes gravity the dominant architect, overwhelming the electromagnetic force and sculpting galaxies. The same fundamental ratio of forces dictates the rules of structure formation. From the tiny quantum world to the vast cosmic arena, it's a single parameter that helps define the boundary between different physical regimes across the universe. This approach gives researchers a spectacularly powerful tool for bridging the gap between the laboratory and the cosmos. By identifying these key dimensionless numbers in a controlled experiment, scientists can make incredibly accurate predictions about how a system will behave under entirely different conditions. A physicist studying the behavior of ultra-cold atoms in a Bose-Einstein condensate here on Earth might be able to draw direct parallels to the behavior of dense matter on a neutron star light years away, because the relevant dimensionless numbers that govern the dynamics are the same. This isn't just a handy trick, it's a profound insight. It suggests that for specific phenomena, the laws of physics are indeed scale invariant. The universe operates in regimes where the absolute size of a system is less important than the balance of forces within it. A whirlpool in your kitchen sink and a hurricane in the Atlantic Ocean can be described by the same fluid dynamics equations when the correct dimensionless parameters are matched. The ultimate goal of this pursuit is to uncover the universe's most fundamental settings. Why does the fine structure constant have the value it does? Why is the ratio of the proton's mass to the electron's mass roughly 1,836? These are not arbitrary numbers. They are the fixed, dimensionless parameters that were seemingly set during the Big Bang, and they dictate everything from the stability of atoms to the lifespan of stars. By studying how these constants create islands of stability and complexity in a vast sea of possible physical laws, we gain vital clues about why our universe is the way it is. The process of dimensional analysis and the search for meaningful dimensionless constants is more than just mathematical bookkeeping. It is a fundamental method for reading the cosmic rulebook, allowing us to see the invisible threads of invariant physical law that weave together the quantum realm and the expanding cosmos. What if our universe, for all its breathtaking grandeur and complexity, is not alone? What if it is just one page in an infinite cosmic library, one bubble in a frothing sea of reality? This is the extraordinary premise of the multiverse concept, an idea that pushes the very notion of a universal blueprint to a staggering meta level. In this view, the patterns we've been tracing aren't just confined to our own cosmic neighborhood. They could be repeating across a vast ensemble of universes, each with its own unique set of rules, yet all potentially built from the same deep mathematical foundations. The mechanism for generating this cosmic plurality often points back to the theory of inflation. We discussed how a scalar field likely drove our universe's explosive early expansion. The theory of eternal inflation suggests this process might never have completely stopped. Instead, it could be a perpetual engine of creation, where the inflating spacetime continues forever, and within it, random quantum fluctuations cause tiny pockets to stop inflating and pinch off to form their own separate bubble universes. Our entire observable cosmos would be just one such bubble, and because each bubble forms through the same basic inflationary mechanism, they might all share similar large-scale properties. They could all be smooth, flat, and possess a cosmic microwave background with similar patterns. In this eternal froth, the multiverse itself could exhibit a fractal-like structure, with bubbles within bubbles, or an endless tree of branching realities, all stemming from a single, never-ending inflationary root. String theory, a leading candidate for a theory of everything, adds another fascinating layer to this idea with its concept of the string theory landscape. The theory suggests there aren't just a handful of ways for the extra dimensions to curl up, but a staggering number, perhaps 10 to the 500 or more different possible stable configurations. Each of these configurations corresponds to a different vacuum state, a different lowest energy setup, which would manifest as a universe with a different set of physical constants and laws. Some of these universes might have stronger gravity, making them collapse instantly. Others might have a weaker nuclear force, preventing atoms from ever forming. But within this unimaginably vast landscape, there will be countless repetitions, the same vacuum state, and thus the same set of physical laws and constants, is likely to appear over and over again across the multiverse. So, while the overall multiverse is a chaotic jungle of possibilities, there could be many universes out there that are nearly identical to our own, or at least similar enough to harbor familiar patterns like galaxies, stars, and perhaps even life. This leads to a truly profound implication. Even if the fundamental constants of nature, the strength of forces, the mass of electrons change from one universe to the next, the underlying equations themselves might remain the same. The language of quantum field theory, general relativity, and the mathematical principles of symmetry and emergence could be universal. A universe with a different value for the fine structure constant would be wildly different from our own, but the equations describing how its electromagnetic field interacts with matter might have the exact same form. This means the patterns we recognize, the way turbulence forms in fluids, the way gravitational collapse leads to hierarchical structure, the way fractal branching optimizes distribution, could be universal truths. They would be the inevitable outcomes of these mathematical principles playing out, regardless of the specific numerical settings. The echoes wouldn't just be visual, they would be deep, structural resonances across the cosmic ensemble. This breathtaking expansion of perspective fundamentally challenges our understanding of uniqueness and pattern. A pattern observed in one place, like the golden ratio in a sunflower, feels special. But if that pattern is replicated across a near-infinite number of universes, does it make it more profound or less so? It transforms the quest for a single, unique blueprint into a search for a meta-blueprint, a set of higher-order mathematical principles that generate all possible blueprints. We are no longer just asking, why is our universe the way it is? But why are all possible universes the way they are? Pondering the multiverse doesn't diminish the wonder of our own reality. Instead, it imbues the very fabric of mathematics with a new and awesome power, suggesting that the patterns we hold so dear are not just the rules of our home, but the immutable laws of a much, much larger reality. Now imagine a grid of squares like an infinite chessboard, where each cell can be in one of two states, alive or dead, on or off. This is the world of cellular automata, and perhaps the most famous example is Conway's game of life. The rules are almost childishly simple. A live cell with 2 or 3 live neighbors survives to the next generation. A dead cell with exactly 3 live neighbors springs to life. In all other cases, cells die or remain dead. That's it. There are no other instructions, no hidden variables. Yet, from this minimalist starting point, an astonishing universe of complexity unfolds. From a random initial configuration, patterns begin to emerge. Some structures stabilize into static blocks or blinking oscillators. Others, known as gliders, become coherent shapes that slowly drift across the grid, persisting over time. Even more complex patterns can act like logic gates, and with enough of them, you can theoretically build a universal computer within the game itself, capable of performing any calculation that a modern laptop can. This isn't just a game. It's a profound demonstration of how intricate, lifelike, and seemingly intelligent behavior can arise from the relentless, iterative application of a few basic, local rules. This incredible property is known as computational universality, the idea that a system, even one with very simple components, can be capable of general computation, meaning it can simulate any other computational process given enough time and resources. The game of life shows that you don't need complex, pre-designed parts to create complexity. You can start with fundamental building blocks and simple laws of interaction, and watch as sophisticated order emerges from the bottom up. This concept shatters the intuition that complexity must be engineered from the top down. Instead, it suggests that the universe might naturally generate richness and novelty through a process of simple rules playing out on a grand canvas. The intricate patterns we see in nature, the branching of a river delta, the spots on a leopard, The arrangement of leaves on a stem might not be individually programmed but could be the natural, emergent output of local physical laws, much like the gliders and oscillators emerging from the digital grid. This leads to a truly radical and provocative hypothesis, championed by physicists and computer scientists like Stephen Wolfram. What if our physical universe itself is fundamentally computational at its core? In this view, the bedrock of reality isn't made of tiny, vibrating strings or minuscule particles, but of information bits. Space and time might not be continuous and smooth, but could instead be discrete, like the pixels on a screen or the cells in an automaton. The laws of physics, which we express as elegant differential equations, might actually be the high-level description of a deeper, digital process, a cosmic cellular automaton running on the ultimate computer. In this digital physics paradigm, every particle interaction, every fluctuation in a field, every passage of time could be the result of a computation, a cell in the universe's grid updating its state based on the states of its neighbors according to a fixed set of rules. The universe wouldn't just contain computations, it would be one. If this speculative vision holds even a grain of truth, it offers a breathtakingly unified explanation for the repeating patterns we've explored throughout this journey. Those fractal coastlines, branching trees, and clustered galaxies wouldn't just be analogous to computer-generated patterns. They would be literally the same phenomenon. They would be the inevitable, emergent output of the universe's underlying code running at different scales and resolutions. The self-similarity we see everywhere would be a natural feature of a system built on recursive, local rules. The universe's blueprint, then, wouldn't be a detailed architectural drawing, but a compact algorithm, a surprisingly short program that, when executed, generates all the complexity we see around us, from the quantum foam to the cosmic web. It's a perspective that transforms our quest for a theory of everything from a search for a final equation into a search for the ultimate algorithm. But this line of thinking leads us to a fascinating and deeply circular puzzle about our own place in the cosmos. Why is it that we, as conscious beings, are even here to notice these patterns in the first place? The values of the universe's fundamental constants appear to be exquisitely, almost miraculously, fine-tuned for the emergence of complexity and life. If the gravitational constant were slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If the force binding atomic nuclei were slightly weaker, hydrogen would be the only element, and stars and planets could never form. This precise calibration has led some to propose a divine architect, but science offers another compelling, if mind-bending, explanation: the Anthropic Principle. In its simplest form, it states that we can only observe a universe that has the conditions necessary for our existence as observers. If the constants were any different, we wouldn't be here to ponder them. This reasoning becomes particularly powerful when paired with the concept of a multiverse. If an infinite variety of universes exist with different physical laws and constants, then it's no surprise that we find ourselves in one of the rare, habitable ones where the numbers just happen to line up perfectly. We are not the purpose of the universe. We are a select audience that has emerged in a corner of reality where the show can be watched. This idea extends beyond just the constants of physics and into the very patterns we've been exploring. Our human minds are exceptionally good at recognizing order. We see faces in clouds, constellations in stars, and symmetrical shapes in natural forms. This isn't a random quirk. It's a product of evolution. Our ancestors, who could quickly identify the repeating pattern of a predator's stripes or the symmetrical form of a nutritious fruit, had a distinct survival advantage. We are, in essence, a species of pattern recognizers, hardwired by natural selection to find structure and meaning in our environment. But here's the profound twist. What if the universe itself is inherently, deeply patterned? Our cognitive hardware for recognizing fractals, spirals, and symmetries didn't evolve in a vacuum. It evolved within a universe that abundantly expresses these very forms. Our minds are tuned to perceive the universe's blueprint because they were forged by that same blueprint. The reason we find the golden ratio beautiful or a fractal coastline compelling might be because these patterns are literally written into the fabric of our reality, and by extension, into the neural pathways of our brains. We don't impose these patterns on a chaotic world. We resonate with an ordered one. This creates a beautiful and mysterious feedback loop between the universe and the observer, blurring the line between ontology, what actually exists, and epistemology, how we come to know it. The universe possesses a certain mathematical order, and we have developed the mental apparatus to decode that order. This raises one of the most enduring questions in the philosophy of science and mathematics. Are we discovering these patterns, or are we inventing them? Is mathematics a human invention, a language we created to describe the world? Or is it a fundamental, pre-existing truth of the universe that we are gradually uncovering? When a physicist writes an equation that predicts a new particle, which is then found years later in a giant detector, it feels very much like a discovery. The patterns seem to be intrinsic, waiting to be found, yet the specific mathematical frameworks we use, calculus, geometry, topology, are human constructs. This interplay suggests that the truth may lie somewhere in the middle. The universe operates on a bedrock of mathematical relationships, and our own pattern-seeking cognition has evolved to construct tools that can interface with that bedrock, allowing us to map its contours with increasing accuracy. This doesn't solve the mystery, it deepens it wonderfully. Our quest to understand the universe's repeating patterns is not a passive observation of an external reality. It is an active conversation. The universe presents a reality structured by mathematical law, and we, as products of that universe, have developed the capacity to listen and respond to that structure. Our very consciousness might be the universe's way of becoming aware of its own design. This transforms the search for a cosmic blueprint from a purely scientific endeavor into a deeply philosophical one, connecting the outer cosmos to our inner cognitive world and suggesting that in understanding the universe, we might also be understanding the deepest nature of our own minds. In the quest to decode the universe's repeating patterns, we now turn to its most enigmatic players, dark matter and dark energy. These invisible components, which together make up about 95% of the cosmos, cannot be seen or touched, yet their influence is written across the heavens in the grandest of designs. Think of dark matter as the universe's hidden scaffolding. We cannot observe it directly because it does not emit, absorb, or reflect light, but we can see its gravitational signature everywhere. Its pull is what prevents rapidly spinning galaxies from flying apart, and on a larger scale, it is the force that sculpted the cosmic web, that vast, intricate network of galaxy filaments and immense voids that stretches across the observable universe. When you look at a map of this large-scale structure, it's impossible not to see the resemblance to other complex networks, like the neural pathways of a brain or the underground mycelial networks of fungi. These systems, though vastly different in scale and substance, all share a common architecture of nodes and connections, suggesting that the universe has a preferred way of building complex, interconnected systems, and dark matter's gravity is the primary architect of that design in the cosmos. The story of dark energy is perhaps even more strange and counterintuitive. While dark matter pulls things together through gravity, dark energy appears to be doing the opposite. It's causing the expansion of the universe to accelerate, pushing galaxies apart from one another at an ever-increasing rate. This wasn't discovered until the late 1990s, and it completely overturned our previous assumption that the cosmic expansion was gradually slowing down. This repulsive force, which seems to be a property of space itself, doesn't just influence the universe's fate. It may also play a crucial role in its evolving patterns. As the universe expands and dark energy becomes more dominant, it could be subtly altering the scaling properties of the cosmos over immense timescales, potentially affecting how matter clusters and how the cosmic web evolves. The interplay between these two dark components is a cosmic tug-of-war that has been ongoing for billions of years. Dark matter's gravity working to pull structures together, while dark energies push works to tear them apart on the largest scales. This dynamic tension is what has shaped, and continues to shape, the universe we see today. What's truly fascinating for our search of universal patterns is how these mysterious entities exhibit their own form of scalability. Take dark matter halos, for instance. These are the immense, diffuse clouds of dark matter that surround and permeate galaxies and galaxy clusters. Detailed computer simulations and gravitational lensing observations reveal something remarkable. The density profile of a dark matter halo around a single galaxy has a mathematical form that is strikingly similar to the profile of a halo surrounding an entire cluster of galaxies. This means that the way dark matter is distributed, from the scale of a single dwarf galaxy to a massive cluster containing thousands of galaxies, follows a predictable, scalable pattern. It's as if the universe uses the same recipe for structuring dark matter, regardless of the size of the final product. Similarly, while dark energy's effects are most obvious on the scale of the entire universe, its influence might also be scale-dependent, subtly influencing the rate at which smaller structures can form within the expanding cosmic background. This scalability hints that these dark components, for all their mystery, operate under rules that produce consistent, repeating patterns. Unraveling the true nature of dark matter and dark energy is not just about solving two separate puzzles. It's about understanding how they work together to create the unified tapestry of reality. Their effects are deeply intertwined with the force of gravity and the expansion of space-time itself. Some of the most ambitious theories in physics, such as modifications to Einstein's theory of general relativity or new types of quantum fields, attempt to explain both phenomena within a single framework. The goal is to find a description that can seamlessly connect the behavior of the quantum world, where particles flicker in and out of existence, with the cosmic scale of galaxies and the accelerating universe. Dark matter and dark energy might be the invisible threads that weave these disparate scales together. They could be the key that finally allows us to see the profound unity between the very small and the very large, revealing that the patterns in a snowflake and the structure of a supercluster are not just analogous, but are different expressions of the same fundamental physical principles playing out across the cosmos. Long before the invention of the telescope or the supercomputer, humanity gazed at the night sky and saw more than just random points of light. They saw a story, a grand design written in the constellations. Ancient civilizations across the globe were the first pattern seekers, meticulously charting the cyclical dance of the heavens and searching for its reflection in their lives on Earth. The Pythagoreans in ancient Greece didn't just hear the pleasant notes of a plucked string. They heard the mathematical harmony of the cosmos itself. They believed that the planets in their motions produced a music of the spheres, an inaudible celestial symphony based on the same mathematical ratios that made a lyre sound beautiful. This wasn't mere superstition. It was a profound philosophical conviction that the universe was built on a foundation of number and form. Similarly, on the other side of the world, Mayan astronomers achieved breathtaking precision in their observations, developing a complex calendar system that wove together the cycles of Venus, the Sun, and the Moon into a single, intricate tapestry of time. They saw these celestial rhythms as deeply connected to the cycles of agriculture, ceremony, and human destiny, believing that the order above was inextricably linked to the order below. This universal human impulse to find meaning in the stars was the very first step on a long journey to understand the cosmic blueprint. This quest for celestial order took a more concrete, geometric form with the work of the Renaissance astronomer Johannes Kepler. Driven by a deep-seated belief in a divine geometric plan, he embarked on a monumental struggle to explain why there were exactly 6 planets and why they orbited at their specific distances from the Sun. His audacious solution was to nest the orbits within the 5 perfect Platonic solids: the cube, tetrahedron, dodecahedron, icosahedron, and octahedron. He proposed that these ideal forms, inscribed within one another, created the invisible scaffolding that held the solar system together. While his specific model was ultimately proven incorrect, Kepler's relentless pursuit was far from a failure. It was this same obsession with finding a mathematical harmony that later led him to his 3 true laws of planetary motion, which correctly described the orbits as ellipses. His story is a powerful testament to the idea that even a wrong theory, if it is driven by a search for beautiful, underlying patterns, can set the stage for a monumental leap forward in our understanding. That great leap arrived with the towering intellect of Isaac Newton. Where Kepler sought geometric perfection, Newton uncovered a universal physical law. In his Principia Mathematica, he demonstrated that the very same force that caused an apple to fall from a tree in England governed the motion of the moon around the Earth and the Earth around the Sun. This was a revolutionary unification. The mechanics of the heavens and the Earth were not separate realms. They were one and the same, obedient to a single mathematical law of universal gravitation. Newton had provided the mechanism, a force acting at a distance, proportional to mass and inverse to the square of distance, that could explain the clockwork motion of the planets. His work didn't just solve the immediate puzzle of orbital motion. It established a new paradigm for all of science. It cemented the powerful idea that the universe is not just orderly, but that its order is written in the language of mathematics, a language we can learn to read through observation and reason. As science progressed into the 20th century, the search for these universal patterns expanded beyond physics and astronomy into the seemingly messy and unpredictable world of biology. This was the great contribution of the Scottish polymath Darcy Wentworth Thompson. In his landmark 1917 book, On Growth and Form, he made a compelling case that the shapes of living things, the spiral of a nautilus shell, the branching of a tree, the hexagonal honeycomb of a beehive, were not arbitrary products of evolution alone. Instead, they were the result of physical forces and mathematical efficiencies acting on living matter. He showed how the form of a jellyfish could be understood through the laws of surface tension, and how the shape of an animal's skull could change according to simple geometric transformations. Thompson was arguing that biology was constrained and guided by the same universal physical laws that governed non-living matter. He was seeing the echoes of scale invariance and fractal-like efficiency in nature long before those terms were ever coined, prefiguring the modern understanding that evolution works with a pre-existing physical toolkit to craft its magnificent forms. This entire historical arc, from the mystical mathematics of the Pythagoreans to the biological insights of Darcy Thompson, reveals something fundamental about our species. We possess an enduring, perhaps innate, fascination with cosmic order and a deep desire to find our place within it. This intellectual journey shows that the search for repeating patterns is not a modern obsession, but has always been the very heartbeat of science and philosophy. It is the thread that connects the stargazing shaman to the theoretical physicist, the ancient astronomer charting Venus to the modern cosmologist mapping the cosmic microwave background. We have always looked up and inward, trying to decode the signals, convinced that the universe is not a chaotic accident but a coherent, patterned whole, and that by understanding its design, we might better understand ourselves. Today's most ambitious scientific inquiries are powered by a remarkable fusion of immense computational power and breathtakingly precise observational tools, allowing us to test these grand ideas of cosmic patterns in ways that were pure fantasy just a generation ago. Take the formation of galaxies, for instance. We can't run a billion-year experiment in a lab, so instead, astrophysicists build virtual universes inside supercomputers. They program in the known laws of physics, gravity, hydrodynamics, the behavior of dark matter, and then set the simulation in motion, watching as trillions of digital particles interact. What emerges from this digital Big Bang is nothing short of astonishing. A cosmic web of dark matter filaments, with galaxies forming at the intersections in clusters and strings that are deeply fractal in their distribution. These simulations don't just produce a vague resemblance. They generate the same statistical self-similarity, the same clustering patterns across different scales, that our telescopes observe in the real universe. This is a powerful validation that the simple, recursive rules of gravity acting on dark matter are sufficient to build the complex, patterned reality we see, directly linking theoretical physics to the observable cosmos. This exploration of patterns isn't confined to the vastness of space. It's equally vibrant at the smallest scales. Advanced microscopes now allow us to peer into the quantum world, imaging structures like quantum dots, tiny semiconductor crystals only a few nanometers wide. When you confine electrons within these dots, they don't behave like little planets. Their wave-like nature dominates, and they form standing wave patterns, much like the electron orbitals surrounding an atom's nucleus, but on a slightly larger, human-made scale. The incredible part is that these man-made quantum states often exhibit symmetries and patterns that feel eerily familiar, echoing the orbital motions of electrons in atoms. We are essentially creating artificial atoms, engineering systems that obey the same fundamental quantum rules and produce similar patterned outputs. This isn't just a laboratory curiosity. It's the foundation for a new generation of quantum computing and advanced electronics, built on our understanding of these universal, small-scale patterns. Perhaps one of the most direct and life-saving applications of this knowledge is in the field of medical diagnostics, particularly with technologies like the magnetic resonance imaging, or MRI, machine. A standard MRI scan produces a detailed image of the body's interior, but the real diagnostic power often comes from analyzing the textures within those images. Healthy biological tissues, from the branching vasculature of the liver to the spongy interior of bones, have a characteristic fractal complexity. Their patterns are not smooth and simple. They are rough, intricate, and statistically self-similar. Diseases like cancer or fibrosis disrupt this natural fractal organization. The tissue architecture becomes more monotonous, more ordered, or more chaotic in a specific way. By using fractal analysis software to quantify the texture of an MRI scan, radiologists can detect these subtle changes far earlier and with greater accuracy than the human eye alone could ever achieve. This means a diagnosis can be made before a tumor has even formed a distinct lump, turning the abstract mathematics of fractals into a powerful tool for saving lives. The principles of scaling and self-similarity have also become indispensable in the world of engineering and design. When NASA engineers design a new space probe, they can't always test a full-scale model in every extreme environment it will face. Instead, they rely on scaling laws, using smaller models and simulations that faithfully represent the full-sized craft, because the underlying physics is scale invariant. The way heat dissipates, the way vibrations travel through a structure, the way fluids flow, these behaviors can be accurately predicted from a scaled experiment if you understand the relevant dimensionless numbers, like the Reynolds number for fluid dynamics. This same logic applies to the opposite end of the scale spectrum in nanotechnology. Designing a nanomachine isn't about simply shrinking a macroscopic device. At the nanoscale, different forces dominate. Surface tension and van der Waals forces can be more important than gravity. Engineers must use their knowledge of how physical laws scale to design entirely new types of structures and motors, building them from the atom up using the new rules that govern the ultra-small. Beyond physics and engineering, the study of complex systems and network theory has exploded, revealing that the universal principles of organization we see in the cosmos apply to human society as well. Ecologists use network models to understand how the loss of a keystone species, a highly connected hub in the food web, can trigger a catastrophic cascade of extinction through an entire ecosystem. Economists analyze the global financial system as a complex network, identifying which banks are so interconnected that their failure could cause a systemic collapse, much like a hub neuron failing in a brain network. City planners even use these principles to design more efficient transportation grids and resource distribution systems, mimicking the fractal, efficient branching patterns found in nature. This cross-pollination of ideas shows that the search for a universal blueprint isn't just an abstract academic exercise. It is a practical, powerful endeavor that is already driving innovation, improving our health, securing our technology, and helping us build a more resilient world, proving that the patterns of the cosmos are not just out there among the stars, but are woven into the very fabric of our daily lives. Yet for all the mesmerizing patterns we find, from the fractal branching of trees to the harmonic ratios in atomic spectra, it's crucial to recognize that the universe is not a perfectly symmetrical, endlessly repeating fractal. There are hard limits to this universality, boundaries where the beautiful repetitions break down and a more complex, less predictable reality takes over. Perhaps the most famous example of this is the Great Divide in modern physics itself. The theory of general relativity gives us a stunningly accurate description of the universe on the largest scales: the warping of spacetime by gravity, the orbits of planets, and the expansion of the cosmos. Meanwhile, quantum mechanics provides an equally powerful framework for the bizarre, probabilistic world of the atom. The problem is, these two pillar theories are fundamentally incompatible. They operate under different rules and use entirely different mathematical languages. This isn't just a technical hurdle. It's a glaring sign that the laws of physics are not scale invariant. The rules that govern the very small are not the same as the rules that govern the very large, and until we find a theory of quantum gravity, this schism remains a powerful counterargument to the idea of a single, universal blueprint. Another significant criticism comes from the field of psychology and philosophy of science. It's possible that we, as humans, are primed to see patterns everywhere, a cognitive bias known as apophenia. We famously see faces in the clouds and animals in the constellations. Could the golden ratio in art and architecture be a case of confirmation bias, where we selectively measure until we find the number we're looking for? Critics suggest that when we gaze at the cosmic web and see a resemblance to a neural network, we might be imposing a familiar biological structure onto an entirely different astronomical phenomenon. We are pattern-recognizing creatures living in a universe that does contain many patterns, and it can be incredibly difficult to untangle which connections are physically real and which are simply projections of our own cognitive preferences. Our very act of observation might be selecting for certain types of order, causing us to overlook the chaos that doesn't fit our narrative. Furthermore, the inherent chaos and randomness woven into the fabric of the universe actively work against perfect self-similarity. Take a fully developed turbulent flow, like the smoke rising from an extinguished candle. While it might appear fractal-like at a glance, its behavior is ultimately chaotic and unpredictable. The immense complexity of the interacting vortices ensures that the pattern never perfectly repeats at a smaller scale. It's unique at every moment. On the quantum level, the phenomenon of decoherence shatters any neat, wave-like patterns. When a quantum system interacts with its environment, its delicate, probabilistic state collapses into a single, definite reality. This process is random and irreversible, breaking the beautiful, scalable symmetry of the quantum wave function and introducing an element of fundamental randomness that cannot be reduced to a simple, repeating equation. This isn't to say the search for patterns is futile, far from it. It simply means that the universe's grand design is more nuanced than a single, repeating fractal. It is a tapestry woven from both threads of elegant order and threads of unpredictable chaos. There are domains where simple rules generate infinite complexity, and there are domains where complexity arises from irreducibly random interactions. Acknowledging these limits is not a defeat. It's a sign of a more mature and complete understanding. It prevents us from falling into the trap of overinterpretation, where we force a pattern where none exists, while still allowing us to stand in genuine awe of the profound connections that do emerge across the scales of reality. The universe is not pure order or pure chaos, but a magnificent and dynamic interplay between the two. So where does this grand quest lead us next? The search for a unified theory of quantum gravity represents the absolute frontier of this endeavor, an attempt to weave the two great pillars of modern physics, general relativity and quantum mechanics, into a single, seamless tapestry. This isn't just an academic exercise. It's a necessary step to understand the most extreme environments in the cosmos, like the infinitesimal singularity at the heart of a black hole or the very first moment of the Big Bang itself, where the laws of physics as we know them break down completely. The leading contenders in this race, string theory and loop quantum gravity, offer radically different but equally mind-bending visions of this ultimate reality. String theory proposes that the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy. Their different vibrational modes, much like the notes on a guitar string, are what manifest as the different particles and forces we observe. This elegant idea naturally requires extra dimensions of space, as many as 10 or 11 curled up into a geometry so small we never perceive them directly. Loop quantum gravity, on the other hand, takes a different approach. It suggests that space and time themselves are not smooth and continuous but are quantized, woven from a fabric of tiny, discrete loops. In this view, spacetime has a granular, atomic structure at the Planck scale, a billionth of a trillionth of a trillionth of a centimeter. Both theories, in their own ways, point toward a reality where spacetime itself might be an emergent property, perhaps even a holographic projection from a deeper, more fundamental layer of information. But these are not merely philosophical ideas confined to chalkboards. They are being pursued through an incredible array of experimental and observational tools that push the very limits of technology. On the incredibly small end of the spectrum, massive particle accelerators like the Large Hadron Collider smash protons together at nearly the speed of light, recreating the conditions of the early universe and searching for signatures of supersymmetry or extra dimensions that could support string theory. Meanwhile, incredibly sensitive tabletop experiments are searching for quantum fluctuations in gravity itself, or for subtle deviations from Newton's law at microscopic distances, which could hint at those hidden extra dimensions. On the grandest scales, a new generation of telescopes is scanning the heavens for clues. The James Webb Space Telescope peers back to the earliest galaxies, studying how they formed and evolved. Gravitational wave observatories like LIGO and Virgo listen to the ripples in spacetime caused by cataclysmic events like black hole mergers, providing a completely new way to test general relativity in its most extreme regime. And precision, measurements of the cosmic microwave background continue to hunt for any faint imprints of primordial gravitational waves, which could carry information from the inflationary epoch, a period where quantum gravity effects were likely dominant. Perhaps one of the most exciting shifts in this pursuit is its increasingly interdisciplinary nature. The recognition of deep patterns is no longer the sole domain of physicists. Biologists, working with physicists, are applying the principles of complexity and emergence to understand how life self-organizes from molecules to ecosystems. Computer scientists and information theorists are collaborating with cosmologists to explore the radical idea that the universe might be fundamentally computational. A vast quantum computation processing information at the most basic level of reality. Neuroscientists are finding that the brain's neural networks optimize their structure with similar efficiency principles to cosmic webs and river deltas, suggesting that the same mathematical rules of network theory might govern how information, matter, and energy flow through vastly different systems. This convergence of fields is creating a powerful new toolkit for discovery, where an insight from one domain can illuminate a stubborn problem in another, revealing a universal logic that transcends traditional academic boundaries. The ultimate hope driving all this research is the discovery of a deeper symmetry or a new fundamental constant that could act as a Rosetta Stone for the cosmos. Just as the principles of gauge symmetry unlocked our understanding of the particle world, a new, more profound symmetry might reveal the hidden connection between gravity and the quantum world. Or perhaps we will find that the constants we think are fundamental, like the fine structure constant, are actually derived from something else, the vibrational modes of a string or the geometry of the compactified dimensions. A successful theory of quantum gravity wouldn't just be another equation. It would be a comprehensive framework that naturally explains why the universe has the scalable, patterned architecture we observe, from the quantum foam to the cosmic web. It would show us that the repeating patterns are not happy accidents, but the inevitable, beautiful consequences of a single, unified set of physical laws. This journey to comprehend the universe's blueprint is far from over. In many ways, it feels like it's just beginning. It is a path filled with more questions than answers, humbling mystery, and breathtaking excitement. It invites everyone, the professional scientist, the curious student, and the awestruck observer gazing at the night sky to participate. Every time we notice a spiral in a seashell and wonder about its echo in a galaxy, every time we ponder the strange connection between a brain cell and the cosmic web, we are engaging in this timeless human quest for understanding. We are not just passive inhabitants of this patterned universe. We are the means by which it becomes conscious of its own profound and beautiful design. From the intricate, fractal branching of a single neuron to the breathtaking, galaxy-laced filaments of the cosmic web, our journey has revealed a universe that seems to whisper the same elegant secrets across every imaginable scale. We've witnessed how the same simple rules, scale, invariance, symmetry, emergence, and the flow of information, weave a common thread through the fabric of reality, connecting the frenetic dance of quantum foam to the stately, gravitational ballet of galactic clusters. This isn't just a collection of interesting coincidences. It is a compelling argument for a profound and deep-seated unity in the cosmos's design. It paints a picture of a reality where breathtaking complexity is not born from endless, arbitrary rules, but emerges naturally and inevitably from a foundation of stunning simplicity. The universe appears to be an expert recycler of its own most effective blueprints, using a common set of mathematical principles to build a tree, a lightning bolt, a lung, and a galaxy. And yet, for all we have uncovered, the greatest mysteries still linger just beyond the light of our understanding. The true nature of dark matter and dark energy, the forces that shape the largest structures of all, remains elusive. The holy grail of a fully unified theory of physics, one that seamlessly blends the quantum world with the cosmic realm, is still a dream on the horizon. But rather than discouraging us, these unanswered questions are what make the pursuit so electrifying. They are the open invitations to further exploration, the reminders that our map of reality is still being drawn. The search for these patterns does more than just satisfy scientific curiosity. It fundamentally enriches our human experience. It invites us to see the world with new eyes, to look at a snowflake and glimpse the structure of a galaxy, to study the veins on a leaf and understand the flow of the universe itself. This perspective transforms the cosmos from a cold, empty void into a place of immense beauty, connection, and wonder. This journey doesn't have to end here. We want to hear how this perspective has shifted your own view of the world around you. Does the idea of a universal blueprint change the way you see everyday patterns in nature? What connections did you find the most surprising or profound? Share your thoughts and reflections in the comments below. Let's continue this conversation together as a community of curious minds. And if this voyage through the scales of reality has captivated your imagination, make sure to subscribe to our channel. We are constantly exploring the greatest mysteries of space, time, and existence, and we'd be thrilled to have you join us for the next adventure into the unknown. Thank you for watching, and keep looking up and down and all around with wonder.